In this project, we're going to implement simple local differential privacy using randomized response from scratch in Python. Specifically, we're actually going to implement in Python the coin flipping example that we just talked about, right? So as you may remember, if you have a group of people that you're wishing to survey about a very taboo behavior, then we give them these interesting instructions as to how they should answer, right? So they flip a coin 2 times, and if the first coin flip is heads, they should answer honestly. However, if the first coin flip is tails, they should answer according to a second coin flip. And what this does is this gives each person plausible deniability while simply averaging across all of their answers with a 50% probability of saying yes or no, right? Thus, if we sample across 1,000 people, we query this over 1,000 people, we interrogate 1,000 people with this question, and around 60% of them answer yes, then we know that the true distribution is 70%, because 70%, the true distribution has been averaged with 50% to get the output of our statistical survey, right? So we want to implement these steps in Python from scratch. And the way that we're going to do this is like so. So the query function we're going to use is a mean function. So we're going to be taking an average. So let's say we have a database of size 10. Well, let's do size 100, okay? So we got a big old database of 100 people. And then the true result is the mean of the database. And here we go. Right? So, and since we generate our database randomly with a 50% probability of being 1 or 0, the mean tends to be around 0.5, right? However, we want to noise our data set using local differential privacy. And local differential privacy is all about adding noise to the data itself, right? So in our case, adding noise to the data means replacing some of these values with random values, right? So if you remember from this randomized response, like sometimes they answer honestly, so these would be the honest results in our example, and sometimes they answer according to a coin flip. So they answer randomly, right? So the first thing we need to do is actually flip 2 coins 100 times, right? So we'll do first coin flip equals torch.rand length of the database greater than 0.5. And we'll go ahead and cast this to a float as well. So now we have our first coin flip for every single value in this database tensor, right? So this is the coin flip for this value, this is the coin flip for this value, this is the coin flip for this value, and so on and so forth, right? And so now let's do this and create a second coin flip. Okay, so now this first coin flip is going to determine whether we want to use the value that's actually in the database or whether we want to use the value that was randomly generated according to this sort of second coin flipper, right? And we can do this to create our sort of noised database or synthetic database or augmented database, we'll call it augmented, in the following way. So half the time, so if a coin flip is 1, right, then we want to use the database. So we'll say heads answer honestly. So we'll call 1 a heads. And the nice thing here is we can do this by simply just multiplying first coin flip by database, because this acts as a mask, right? So the multiplying it times a 1 will leave in whatever the database is, and multiplying it times a 0 will zero out any values in the database, right? So this will return database times first coin flip returns a 1 only for the places in the database where there actually was a 1 originally. Oh, gotta cast this to a float again. Okay, so here's all the 1s and a few of the 0s that were in the original database that the first coin flip says we should keep around, right? But now, sometimes we need to lie, right? So sometimes we need to choose randomly. So if our 1 minus our first coin flip, here's all the places where we want to actually choose randomly. So all these 1s that you see here, we want to actually sample from the second coin flip. So we can do this by simply sampling or multiplying times the second coin flip, right? So here's all the values that are being sampled randomly. And so now if we simply add these together, then we get a new augmented database, which is differentially private. Cool? So far, so good. So again, local differential privacy is all about adding noise to the database entries so that any queries that we do in this database have a certain amount of differential privacy. However, in doing so, we have done something statistically significant, right? So we might try to say, oh, we can just query this database and be done. So torch.mean, database.float, and boom, we augment the database. And we can just go ahead and use this. However, something else has happened here. So half of our values are honest, and half of our values are always going to have a mean, or try to have a mean, that's at 0.5, right? This means that it's going to skew the output of our query towards 0.5, because half the time we're using the values that are from this second coin flip, which is a 50-50 chance of being positive or being heads or tails, right? So let's just say the database had, on average, it was 70% of the time that people said true, right, for whatever the taboo behavior was. So this database is actual values reflecting from people, right? And let's say that 70% of these were true, okay? So that the mean of this would be 0.7. That would mean that if we took half the values from here and half the values from this randomly generated, 50-50 distribution, then the mean of them would shift from this, where the mean was 0.7, and this, where the mean was 0.5. It would be halvesies between them, right? The mean would then be 0.6, even though the original distribution was 0.7, right? So it's almost like this query is now skewed as a result of the noise. Skewing was not what we were after. What we wanted to do was just give each individual person plausible deniability. So we have to do one final step here, which is to de-skew the result, right? So, and the interesting thing is here, if we know that, say for example, there's a distribution here, right, where there's a certain average that's here, and we'll say it's 70%. And the average of this is always going to be 50%, so that we know that the average between these two data sets, right, if we are half from here and half from here, is 60%, then we can just do that in reverse, right? So that means that if the output of our augmented database gives us a mean of 60%, well then we know that it's really trying to tell us 70%, because half of our data is just 50-50 random noise, right? So I can actually go and try to de-skew this result, and this is the true output of our database, right? Because I have removed the skewed average that was a result of this local differential privacy. It was a result of these second coin flips. So this is actually the output of our augmented result, right? So our augmented differential private result, right? Yeah, we'll call it DP result. Cool. So now we can package all this as a single query and see what was in our assignment. So in our assignment, we needed to return the augmented result, the differentially private result. We also wanted to return the true result, because the notion of this and what we wanted to learn from this lesson is actually to understand how these results tend to change. So let's go ahead and return the true result, or compute the true result as well. And here we go. Okay, and so now what we want to do here is work on databases of different sizes. So I believe in the assignment we were supposed to do a database of size 10, and then look at the private result, true result. We'll print this out here so it's easy to see. So with noise and without noise, meaning this is the true answer, right? And what we're going to see when we compare these is that, man, that noise really throws things off sometimes, right? But let's use a bigger data set. Oh, okay, that's quite a bit closer. Let's use an even bigger data set. Ooh, now we're getting really close. And an even bigger data set. So we'll put 10,000 entries. And now these are getting really close. So here's the thing to remember about local differential privacy, and really actually about differential privacy in general. Whenever we're adding noise to a distribution, we're corrupting it, right? And so the statistics, the queries that we're doing are going to be sensitive to this noise. However, the more data points that we have, the more this noise will tend to sort of average out. It will tend to not affect the output of the query, because on average across a large number of people, sometimes the noise is making the result higher than it should be or lower than the result should be. But on average, it's actually still centered around the same mean of the true data distribution. And in particular, a general rule of thumb, which is local differential privacy, is very data hungry. In order to be able to noise the data set, you're adding a ton of noise, because we're adding noise to every single value in the data set, right? So when we have 10,000 entries, we're adding 10,000 bits of noise. I guess probably with 50% probability, so it's probably more like 5,000 bits of noise, but that's still a lot of noise. So global differential privacy, in contrast, only adds noise to the output of the query. we will find that this tends to be quite a bit more accurate and a little less data hungry than local differential privacy. So if you want to implement local differential privacy and protect data at the data level, right, protect the data set itself, then you'll want to use local differential privacy, but you want to make sure you have a really large data set. Whereas if you want to use a less data hungry algorithm, so maybe your data set's smaller, but you still need to be able to protect it, then it's better to lean towards global differential privacy. And in general, I think, personally, leaning towards global differential privacy seems to be where a lot of the field is going, although obviously local DP has its advantages, right? So the advantage of local DP is that in theory you could publish some of these data sets, or you don't have to trust someone to, there's lower trust settings. We'll get into those later. But for now, just understand this notion of this trade-off between sort of small data sets and large data sets, meaning that your noise creates vastly different outputs of the queries versus only slightly different outputs of the queries when you have a large enough data set to average the noise over.